We've actually worked quite a bit with matrices already. We've worked with them in terms of solving systems of equations. We haven't looked at adding and subtracting, multiplying matrices. What we've done is looked at row operations. So all of our work so far has been basically operations on rows of a matrix, but not on the matrix itself. So to get started, first of all, let's go ahead and look at some notations for matrices and go over some other material that we've already talked a little bit about before, but we'll want to make sure we understand before we go any further. When we have an array of numbers arranged in rows and columns like we've looked at before, and they're placed in brackets, that's basically called a matrix. And we can represent a matrix in two different ways. First of all, we can use a capital letter to denote a matrix, so we might have matrix A, or of course we can use any other letter as well. Or we can also use a lowercase letter enclosed in brackets. So we might use A, and in this case we could use IJ. Now we're already familiar with the IJ notation. The IJ represents the number of rows and columns. So AIJ is basically representing here the general element in the matrix in the ith row, jth column. So again, if we had something like A32, this is the element of the matrix A that is located in the third row, second column. When we talk about the order of a matrix, we're talking about, let's say, a matrix that might be 3 by 4. The order of the matrix is 3 by 4. 3 rows, 4 columns. And again, it's always rows and columns. Those never switch around. If rows and columns are the same, then basically we have a square matrix. So first of all, using matrix notation, let's go ahead and talk about the elements of a particular matrix. So for this example, we're looking at the matrix A, and we can see here that I have 2 rows and 3 columns. So when we talk about what is the order of A, because it's 2 rows and 3 columns, it is an order of 2 by 3. So A is the matrix that has 2 rows and 3 columns, so the order is 2 by 3, or it's a 2 by 3 matrix. Now in this notation that we have down here, what is the element A23? Well, 2 refers to the second row, so here we are, here's first row, here's the second row, and in the second row I'd like to look at the element from the third column, so A23 would be second row, third column intersection would be a negative 1/5. So in this case, A23 is a negative 1/5. Now A12 would be the first row, second column. So here's my first row, second column. The intersection is 2, so A12 is equal to 2. So it's pretty easy to work with matrices. We want to make sure that we understand when we're talking about elements that we can refer to them, so it's important to use that terminology. The next thing we're going to do is talk about the equality of matrices. Basically, 2 matrices are equal if and only if they have the same order and the corresponding elements are all equal. So those are the 2 criteria that must be true. Both the order and the elements, the corresponding elements, have to be equal. So let's go ahead and look at an example using equality of matrices. So using the definition of equal matrices, let's go ahead and look at an example where we have a matrix A is equal to, it's a square matrix, 2 by 2, x, y plus 1 in my first row, and z, 6 in my second row. And we'll also look at a matrix B that is a square matrix, 1, 5, 3, and 6. Now the first thing we note is they do have the same order. So if you look up here, equality of matrices, matrix A equals matrix B if and only if A and B have the same order. That's our first criteria. Well, if you notice here for matrix A, the order is 2 by 2, and for matrix B, the order is 2 by 2 as well. So both have the same order. So both of these have an order of 2 by 2. And then I need to say, okay, well, they're only equal if all the corresponding elements are equal. Well, these may or may not be equal depending on what x, y, and z are. So let's go ahead and look at this in terms of forcing this to be equal. So A matrix and B matrix will only be equal if x is equal to 1, if y plus 1 is equal to its corresponding element in B matrix, which is 5, and if z equals the corresponding element over here, which is 3. And of course, in this last position, A22, we already have 6 equals 6. So it looks like to me, x equal 1, we're already done with that. Y in this case would have to be equal to 4. We'd subtract 1. Z is already equal to 3, and 6 is equal to 6. So I'm kind of thinking about these kind of in a vague sense, like this. These are not actually matrices, but it's talking about the positions of each one. So under these conditions, A equal B, matrix A equals matrix B, if x is 1, y is 4, and z is 3. So now I have equivalent matrices. The next thing we're going to look at is how do you add and subtract matrices. When we're working with matrix addition and subtraction, one of the most important things to remember is you can only add or subtract matrices that have the same order. If they do not have the same order, you cannot add or subtract them. So when we're talking about matrix addition, the first thing we need to make sure is that the matrices have the same order that I'm trying to add together. The same thing will work with subtraction as well, but we'll just focus in on addition first. So for matrix addition, matrices of the same order are added by adding the elements in corresponding positions. So the first thing to check for when you're adding matrices is that they're the same order. If they're the same order, then add the corresponding elements together. So let's go ahead and look at an example with matrix addition. So we'll look at two matrices. We're going to use a nice little 2 by 2 matrix again. And we want to add this to another matrix. And the first thing we want to do is to say, okay, are these matrices of the same order? Well, if we look at this first matrix, it's 2 by 2. Second matrix is 2 by 2, so check they are of the same order. So now we can just combine the corresponding elements. So to get my solution here of what is the sum of, let's say, matrix A and B, I would take 1 plus a negative 1, which is 0. Negative 2 plus 6, which is 4. 3 plus 0, which is 3. 5 plus 4, which is 9. And this is the sum of those two matrices. Now, matrix subtraction is identical to matrix addition, with the only difference being that when you subtract matrices, they have to be of the same order as usual, but then we subtract the corresponding elements. Now, of course, when you're adding two matrices, order doesn't matter how you add them because the corresponding elements will add the same. Order does matter when you subtract matrices and with any other values as well. So matrices of the same order, and again they have to be of the same order, are not added here, I have added, are subtracted by subtracting the elements in the corresponding positions. So let's go ahead and look at an example of subtracting matrices. So for our first one, let's go ahead and look at a familiar matrix, one that we did same as above, but instead of addition we're going to be looking at subtraction here. No order matters when you subtract numbers and when you subtract matrices. So here, when we are finding our difference, we take 1 minus a negative 1, which is the same as 1 plus 1, which is 2. Negative 2 minus 6, which is the same as minus 2 minus 6 is minus 8. 3 minus 0, which is 3. And 5 minus 4, which is 1. So this matrix gives us the difference. Now, what do we do if the order is different? They do not have the same order. What would we do? Well, first of all, you can add three matrices together. You'd have matrix A plus B plus C. They would all have to be of the same order. Now, if we were combining a lot of matrices and taking, let's say, A minus B minus C, they would all have to be of the same order. But what do we do if the sum or the difference of two or more matrices of different order? We couldn't do it. So let's look at an example here. So let's say we are trying to take 0, 3, 4, 3, which is a 2 by 2 matrix, and add it to, let's say, this matrix, 1, 9, 4, 5, 2, 3. So this matrix is 2 by 2. This matrix is 3 by 2. And it doesn't make sense to work with these. So first of all, they're not of the same order. So we're kind of done with our definition. But more importantly, even if we did think they were of the same order, how would I combine the corresponding elements? It looks like 0 corresponds to 1, 3 corresponds to 9, 4 corresponds to 4, 3 corresponds to 5, but then what corresponds to the 2 and the 3? It wouldn't make sense. So you cannot add or subtract matrices unless they are of the same order. Now we're going to look at a couple special case matrices as well before we move on. The first one that we're going to look at is called the zero matrix. Now the zero matrix is similar to other values that we've looked at called like an additive identity. If you take 1 plus 0, you get 1. So 0 is called the additive identity. Well, the zero matrix has the overall same effect. So a matrix whose elements are all equal to 0 is called the zero matrix. So let's go ahead and look at what a zero matrix would look like. So to start with here, we could produce, let's say, a 2 by 2 matrix. A 2 by 2 zero matrix would look something like this. And we could add it to some other matrix. Now this matrix would have to be of the same dimensions, so both of these are 2 by 2, 2 by 2, because if they're not of the same dimensions or the same orders, I can't combine them. And if you look at this, when I add the corresponding elements, I get the same original matrix back. So this 2 by 2 matrix right here is called the additive identity. When I add it to a matrix, I just get the original matrix back. So it's called the additive identity. The next one that we want to look at is called the additive inverse. Now the additive inverse we're also familiar with working with numerical values. If I have a 2, a negative 2 is the additive inverse because when I combine it with 2 I get 0 back. So basically the additive inverse of matrix A is negative A. So if we had a matrix, let's say like 5, 4, 3, 2, the question is, what would we combine this matrix with to get the zero matrix? Well, first of all, we know it's going to be the zero matrix that's 2 by 2 because this original is. And we also know that this additive inverse matrix has to be a 2 by 2 as well. And then what you do is you negate all the values in your original matrix. So we'd have negative 5, negative 4, negative 3, negative 2. And when we combine these, I do get 0. So I have the additive identity. So this matrix is the additive identity. Now it's going to change from matrix to matrix, of course. For this example, it's the additive identity. So another way we can think about this is if we have matrix A, what would I add to matrix A to get 0? You would add the negative of matrix A to get 0. So again, it's the additive identity. Now we've talked about some of these properties with the zero matrix and the additive inverse. We also talked about how order didn't matter when you were adding but did matter when you were subtracting. So let's go ahead and look at some of these properties of matrix addition. Now these will be very similar to properties that you've already learned of numbers. So first of all, when you are adding two matrices, order doesn't matter. So A plus B equals B plus A. Now this is called the commutative property of addition. Now be careful here. Please understand that A and B are matrices. Next we have A plus B in parentheses plus C is equal to A plus in parentheses B plus C. Now what does this mean? Well, remember PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. That would mean I would do these parentheses first. Well, the same thing's happening here, is saying, you know what, it doesn't matter what we do first. This is the associative property of addition. Now this is of course applied to matrices. Now what this is meaning is, again, order doesn't matter in this first line, and in the second line order doesn't matter either, but we're taking into account a possibility of more than two matrices. Next we have what we just got done talking about. A plus 0 is equal to 0 plus A, which is just equal to A, of course. This is the Additive Identity property. If you add the 0 matrix to any matrix, you get that matrix back. Next we have A plus a negative A is equal to negative A plus A, this is the commutative property, which equals 0, the additive inverse property. So those are some properties of matrix addition. Now of course, A, B, and C, the matrices that we're looking at here, are all of the same order or all of the same dimensions. Next we're going to look at scalar multiplication. Now before we can actually start talking about scalar multiplication, we probably better define what a scalar is. First of all, we could have a 1 by 1 matrix, which would mean it would have exactly one entry, like this value of 6, let's say. Well, this is a matrix. It's a 1 by 1 matrix, and it contains only one entry. Now what we need to do is make sure we know how to distinguish this matrix from just the plain old number 6 or a scalar. So we also have a scalar value of 6. Now notice this is a matrix, one element matrix. This is just a number or a scalar. Now to multiply a matrix by a scalar, you multiply each entry in the matrix by whatever that scalar is. So for example, I could take 4, which is a scalar, times a matrix, let's say 2, 5, negative 3, 0. In order to do this, you would just take that scalar times each of the entries we have here. 4 times negative 3 and 4 times 0. Now notice the dimensions or the order of this matrix 2 by 2 will equal the dimensions or the order of the matrix when you're done. So in this case we have 8, 20, negative 12, 0. So again, the order doesn't change here. Now we're going to be looking at scalars when we are solving some of these and working with some of these values. So it's important to be able to look at these in terms of scalar multiplication. Now when we would put a 4 out front, before we would actually be taking like 4 times R1, so we'd have an R1 notation. This 4 out front means we want to take 4 times the entire matrix. Now there's also particular properties of scalar multiplication as well. So the properties of scalar multiplication, if you have, let's say, 2 scalar values, CD, times a matrix A, and remember use a capital letter to represent a matrix, that means that I could also take C times DA, meaning order doesn't matter. So this is called the associative property of scalar multiplication. Now the word scalar here is important because this property might not apply with just strict multiplication of matrices. We're only looking at scalar multiplication right now. Now if you take 1 times anything, you'll get that self back. So 1 times the matrix A will just equal A, and this is called the scalar identity matrix, or the scalar identity property, sorry. If we have a scalar out front of adding together 2 matrices, or the sum of a matrix, I can distribute the scalar through the sum. So this is called the distributive property. And this would work with addition or subtraction. And if I had a sum of scalars times a matrix, I can distribute the matrix through the sum of the scalars. So this would be CA plus DA, where A is a matrix. And this is also the distributive property. It's just a matter of whether we're distributing through a sum of scalars or a sum of matrices. Now we've already talked about solving linear equations, but next we want to go ahead and start solving a matrix equation. So for this example, let's go ahead and look at solving a matrix equation. Now before we can actually solve a matrix equation, we should probably have a look at one and see if it makes even sense to start setting this up. Now whether a number is out front or on the other side, I need to make sure that it's distributed through the entire matrix. So 2x means 2, it's a scalar 2, times the matrix x. Another thing to keep in mind, anything that's capital letter is actually an entire matrix. Now what we want to do is to solve for x in this matrix equation. When, let's say, we have two matrices, A is equal to 1, negative 5, 0, 2, and B is equal to negative 6, 5, 9, 1. So first of all, we begin by solving the matrix for the equation x, just like we would in regular old algebra, and then we kind of work from there. So let's go 2x plus A equal B. I think the smart thing to do would probably be to subtract A from both sides and then divide both sides through by 2. So we get x, the matrix x, it's a capital X, is equal to B minus A over 2. Another way we could look at this is 1/2 times B minus A. So it looks like to me if we could take the difference between matrix B and matrix A and then take that times a scalar of 1/2, that would be our solution. So let's go ahead and have a look and see what x equals. Now remember, in order for this to work, B and A have to have the same dimension. So I have a 1/2 out front. Let me change my parentheses here a little bit. 1/2 out front, and then B, matrix B, is negative 6, 5, 9, 1, minus matrix A, 1, negative 5, 0, 2. Now what has to happen here is, first of all, they have to be of the same dimension, and they're both 2 by 2, so this works well. Okay, scalar value is out front. If I wanted to, I could take the 1/2 and distribute it through, but I'll just go ahead and perform the matrix subtraction first. So here we have minus 6 minus 1 is minus 7. 5 minus a negative 5 is the same as 5 plus 5, which is 10. 9 minus 0 is 9. 1 minus 2 is negative 1. And then to finish this off, I get x is equal to, I go ahead and multiply each element by 1/2. I get negative 7/2, 9/2, 10/2, which of course is 5, and negative 1/2. And this is the matrix that's the solution to that equation, 2x plus A equal B, if A and B are equal to those particular matrices. Now we could check this. I could take this matrix X and plug it in up here, multiply by the scalar of 2, add A, and I should get B back. So again, it's important to remember that you can actually check these types of solutions. The next thing we're going to look at is matrix multiplication. Matrix multiplication is a little bit more involved than some of the other operations that we've performed so far. So, matrix multiplication. Now, when we have matrix multiplication, we do not multiply two matrices by multiplying the corresponding entries. So, you know, when we subtracted these, we just subtracted the corresponding entries. That's not how you work with matrix multiplication. Also, with matrix multiplication, the order does not need to be the same for the matrices. However, they do need to have some certain characteristics in order to be able to multiply the two matrices together. So first of all, let's go ahead and work with a simple 2 by 2 matrix when we're talking about matrix multiplication, and then we will increase that to a little bit more complicated non-square situation. So let's go ahead and start with square matrices first. Now we're trying to multiply two square matrices. Now if we're going to multiply A times B, matrix A times matrix B, let's go ahead and write out what that would look like. I'm just going to make up some matrices for A and B here. Let's call this elements A, B, C, D, E, F, G, H. So when we multiply these together, for the first element of my solution matrix, basically what we do is we take A times E plus B times G. So again, that's A, E plus B, G. So again, that's A, E plus B, G. That will be the first element in my solution matrix. Next thing, we take the first row times the second column in the similar manner. So we take A, F plus B, H. A, F plus B, H. This is the second element in the first row of my solution matrix. Now we're done using this first row. Now let's go to the second row. Similar manner. You're going to take second row times the first column. That will be C, E plus D, G. That's the first element of the second row. Next we'll have C, F plus D, H. So whatever those elements are for A through H, I would multiply them and add them in this fashion, and that would give me my solution matrix. And I think after you do a few of these, it's going to become pretty obvious what's going on, but we could talk our way through this as well. The first step in this is we multiply each element in row 1 by the corresponding element in column 1 of B. So I take A times E and B times G, and then I would add these products together and then record the sum as the element in row 1, column 1 of the product or solution matrix. And then you would keep going through the same process over and over again. Now these are 2 by 2 matrices, so they're pretty easy to work with. Now remember, this was 2 by 2 and 2 by 2. Well, apparently the only way that this is going to be able to work for any other dimensions of matrices are if these two values are the same in the middle. So let's go ahead and have a look at that and see if that makes sense. So we're going to go to non-square matrices. Now for non-square matrices, okay. So let's go ahead and make up two matrices. Let's say A would be 2 by 3 and B would, let's say, be 4 by 1. And I want to look at their product, A, B. So let's have a look and see what that could look like. 2 rows, 3 columns. A, B, C, D, E, F. 2 rows, 3 columns times 4 by 1. 4 rows, 1 column. G, H, I, J. Now if we go through that same process, we'll say, okay, we'll take A times G plus B times H plus C times I. But notice we run out of values here. So again, this was dimension 2 by 3. This was 4 by 1. So the only way that this could work is if the number of columns is equal to the number of rows of the second matrix. So this will not work because I don't have that particular relationship between the rows and the columns of the two corresponding matrices. So for the product of two matrices to be defined, the number of columns of the first matrix must equal the number of rows for the second matrix. Now let's look at this definition a little bit closer. So let's say we had two matrices, matrix A, which we'll say was some generic M by N, and some other matrix B with some N by P dimension. So the number of columns in this first matrix is equal to the number of rows in the second matrix, so I can get a solution here. And as it turns out, when I consider the product AB, the solution for the product AB, and I'll put these in parentheses so I can show that they're a product, would be M by P, would be my solution matrix. So the ends, essentially cancel each other out, and you're left with a matrix that's M by P for your solution matrix. I think the best way is to go through and look at some examples for these. So let's go ahead and look at an example of a non-square matrix being multiplied by another non-square matrix. So let's go ahead and look at A is 1, 2, 3, and matrix B is 4, 5, 6. Now, if you talk about A, the dimensions for A are 1 by 3. The dimensions for B is not 1 by 3, but it's 3 rows by 1 column, so it's 3 by 1. So we can see right away here, let's say we want to find the product AB here. Can I find the product AB? Well, does the number of columns in the first matrix equal the number of rows in the second matrix? And the answer is yes, so I should be able to multiply these. So let's go ahead and go through and do that, and then we'll also look at B times A, and then we'll try and decide if they're equivalent statements or not. So to start with here, I can perform matrix multiplication, and the answer to this is going to be 1 by 1. So I'm going to get a 1 by 1 matrix out of this. So let's go ahead and go through and multiply these. A is 1, 2, 3. And B is 4, 5, 6. So again, I know my answer is going to be a single entry matrix or a single element matrix. And that single element is going to be 1 times 4 plus 2 times 5 plus 3 times 6. Now notice there's no spaces, no commas. I'm multiplying, adding all these together. So if we do that, I get 4 plus 10 plus 18, which is 32. Now this is not a scalar, this is a 1 by 1 matrix. So 32 is the only element of this matrix, and it is a 1 by 1 matrix, and so this kind of matched up with what I thought we should get before we even got started here. Next part I'd like to do here is to look at B times A. Now when we look at B times A, we'll start to figure out whether I have order mattering or not mattering when we are talking about matrix multiplication. Now remember, order didn't matter when we added, order did matter when we subtracted. So this is B times A. Now this is interesting. B times A. So B is 3 by 1. A is 1 by 3. The number of columns in the first matrix is equal to the number of rows in the second matrix. So I can look at this in terms of, yes, multiplication can be performed with these two matrices. Now let's look and see what my answer will be. Will it be a single term? Is it going to be a 1 by 1? No. It's going to be a 3 by 3 will be my answer. And that's pretty amazing, because you're thinking, well, it should come out to be the same or something similar, but not at all in this particular case. So right away we know order matters when you're multiplying matrices. When you take 2 times 3, you get 3 times 2. So order doesn't matter when we're multiplying scalars, but it does matter when we're multiplying matrices. So I know I'm going to get a 3 by 3 here. Well, in this first top left element, that'll be 4 times 1. Next element, I will have 5 times 1. Next element will be 6 times 1. Now we're working on the second column. I'll have 4 times 2, 5 times 2, and 6 times 2. And then I'll have, for my last one, I haven't used the 3 yet. So I'll have 4 times 3, 5 times 3, and 6 times 3. So this is a 3 by 3 matrix. Let's go ahead and write out what it will look like when I actually multiply those values out. I'll get 4, 5, 6, 8, 10, 12, 12, 15, 18. This is my solution matrix. This definitely does not equal 32. This is a 3 by 3 matrix. This is a single matrix or a single element matrix. So order does matter when you're multiplying matrices. So for matrices, AB does not equal BA. So make sure you keep that in mind. Order matters when you're multiplying matrices. Okay, let's go ahead and look at another example of matrix multiplication. Okay, first of all, let's go ahead and let's look at the matrices. 1, 0, 2, 2, 3, -1, 4, 6, let's say, times 4, 2, 1, 3. So before we even get started, we need to check the dimensions or the order of the matrices. This matrix is 2 by 4. This one is 2 by 2. The number of columns in the first matrix does not equal the number of rows in the second matrix, so 4 does not equal 2 here. Therefore, matrix multiplication for this scenario is undefined. So we cannot perform matrix multiplication here. Because the dimensions don't match. I'd have to take 1 times 4 plus 2 times 1 plus 3 times, oops, there's nothing down here, so I can't do that. Run out of space there. Let's go ahead and look at the same matrices, but let's just change the order. Let's put them 4, 1, 2, 3, and then 1, 0, 2, 2, 3, -1, 4, 6. And let's see if we can perform matrix multiplication here. So this is 2 by 2. This is 2 by 4. The number of columns in the first matrix is equal to the number of rows in the second, so I can perform matrix multiplication here. And my answer, remember these 2's in the middle will kind of cancel each other out, should be 2 by 4. Whatever that solution matrix is or the answer matrix is. So let's go ahead and figure out what those elements are of the solutions. I would take 4 times 1 plus 2 times 0. So 4 times 1 plus 2 times 0 is 4. For the element down below, I would take 4 times, or sorry, I already did the 4 times 1 plus 2 times 0. So the element down below, I take 1 times 1 plus 3 times 0. So 1 plus 1 plus 3 times 0 is 1. Okay, working across, I'm going to take 4 times 2 plus 2 times 2. 4 times 2 is 8. 2 times 2 is 4. 8 plus 4 is 12. So that would be my next element. Next, we're going to go 1 times 2 plus 3 times 2. So that would be 1 times 2 is 2, 3 times 2 is 6, 2 plus 6 is 8. And you would continue this process until you got your 2 by 4 matrix. So when the dimensions are not square, it makes it a little bit more difficult to work with. Now, just like we looked at properties of scalars and properties of matrix addition and matrix addition, we didn't look at any properties of subtraction. Let's go ahead and look at properties of not scalar multiplication, but properties of matrix multiplication. Now we already know one of them. AB does not equal BA. So let's not put that one here because it's not one of the properties. So AB times C, and remember A, B, and C are all matrices. This stands for the associative property of matrix multiplication. And of course, for this to work, all of the dimensions are going to have to match up. So if we have 3 dimensions that are matching up here, it doesn't matter if we take A times B first or B times C first. So this is the associative property of matrix multiplication. Okay, next we have A times the sum of B plus C is equal to AB plus AC, the distributive property. So this is the distributive property of matrix multiplication. This would also work if we rewrote this a bit. AC plus BC. And of course, for any of these to work, all the dimensions are going to have to kind of cooperate here. Now I'll also bring up scalars. If I have a scalar times a product of matrices, that's the same as saying I could take the scalar times the first matrice times the second matrice. And it looks like I better plug in my battery here in a second. This is called the associative property of matrix multiplication. Or sorry, of scalar multiplication, because we have that scalar involved. So these are all the operations that we're looking at. We're not talking about division because I haven't talked about inverses yet. So these are all of the operations that we can be looking at, and that was kind of the point of this lecture, was matrix operations. What we haven't looked at are any particular applications, and I would like to look at a couple of applications before we finish. So for this example, we're going to be looking at kind of an application with the idea of using pixels in digital photography. So a still image that you look at on the internet, or even are taking with a camera, it's in a digital format, and it's made up of lots and lots and lots of pixels. And pixels are created by basically taking an image and dividing it into a grid, and then the computer can change the brightness or the color of every single little pixel in the grid. Now this picture right down here is kind of a blown up 3x3 grid, and each of these values, these huge values, is a pixel. So in this particular case we have 9 pixels. Now again, in this case we have the letter L here in the left hand side, the letter L, and the letter L is made up of these 4 green pixels. The number 2 represents a pixel that's green, the number 3 represents a pixel that's blue, the number 1 represents a pixel that's red, and the number 0 represents a pixel that is plain white or empty, however you want to look at that. So what I would like to do first of all is find a matrix that represents a digital photograph of the letter L giving these color levels and this criteria, and then I would like to decide how can we change the contrast of this letter L in a particular way. So first of all, let's go ahead and come up with a matrix that represents this letter L. Well, first of all, this is a 3x3 grid made up of 9 pixels, and so I think a 3x3 matrix would do a good job to explain this. In the top left element, I'll have the number 2 because I have a green pixel, and I have green pixels below that as well. Across the second column, or down the second column, I have red, red, green, which would be 1, 1, 2. And then the third column is red, 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 1, 1, 1. So this is a matrix that represents that letter L. Now what I want to do is I want to think about transforming this letter L, same letter L, but different colors. So I would like to transform this and then determine what operation would have to be performed on the first matrix to get our final matrix. So what I'd like to do is I'd like to take this design that we have up here of this green L with the red other colors, and I would like to transform it into this blue L with white where the red used to be. So let's go ahead and write a matrix that represents this particular picture. This is still a 3x3. Everywhere there's a blue, I'll have the 3 for my color level. And then everywhere there's a white, that's my color level 0. So I want to take this 2, 2, 2, 1, 1, 2, 1, 1, 1, transform it into 3, 3, 3, 0, 0, 3, 0, 0, 0. So the question is how would we do that? Well, let's go ahead and start with our 2, 2, 2, 1, 1, 2, 1, 1, 1. Okay, how would we change this? This is kind of our unknown right here. We know it has to be a 3x3 because when you add matrices, you have to have the same dimensions. And I want to get 3, 3, 3, 0, 0, 3, 0, 0, 0. Now this is not like solving linear equations. In solving linear equations, I was trying to get it in row echelon form. I was trying to perform row operations. But what we want to think about is how can I switch this 2 to a 3 right here. Well, I think that we can change the 2 to a 3 by adding 1. So this is solving a matrix equation as well. It just has a little bit different application. 2 transfers to a 3 by adding 1. 2 to 3 is a 1. And then how do we get from 1 to this 0? We subtract 1. And that's going to be the true value for all of these. And then of course 2 transfers to 3 by a 1. So this is my solution matrix in this particular case. So we can change our green and red L pixel picture to this blue and white pixel picture with this transformation. And so when you change the colors in one of your documents or one of your shapes, or you see a change in a picture, this is the process that can be going through. There's some other really interesting applications of matrix operations as well, but I think this is enough to get us started.